Welcome to Tech Talks, Lecture 123, designing with a LM7810 1 amp regulator. The LM7810 supply converts a high voltage AC source into a stable regulated 10 volts DC output. It is ideal for hobbyist projects and embedded systems like the Arduino and other microcontrollers that require a consistent 10 volt DC supply. The design uses a transformer, a rectifier, a smoothing capacitor, references a bulk capacitance, the LM7810 with smoothing output capacitances. Selection of the AC in VN must be set to 2 volts higher than 10 volt DC regulated output. Thus aids in the selection of the step-down transformer that will be chosen. Usually a transformer that steps down 120 volts AC to 25 volts AC will work, but you could go as low as 12.5 AC peak voltage. Here we're going over the electrical characterization of the Micro A 7800 series positive voltage regulators. These regulators are industrial standard, and they are like the LM7810 family series or LM7800 series. There are 3 terminal devices. Each device has an output current up to 1.5 amp, internal thermal overload protection, high power dissipation capability, internal short circuit current limiting, that is if the output gets shorted to ground, it'll shut down, output transistor safe area compensation. As you can see, it's a TO220 package where the pin 1, looking down on the device, is input, pin 2 is common, and pin 3 is the output. They have an associated family of integrated voltage regulators for a wide range of applications. They have 5 volts to 24 volts, made by Texas Instruments. Here is the silicon schematic of inside the chip. We won't be going over that. Now we have some thermal data with relation to the package, the TO220 package. This is the one we're interested in, the 19 degrees Celsius per watt, and that'll help us determine if we need a heat sink or not. You can use Celsius or centigrade. Centigrade is an older term, and today most people use Celsius. Here is our positive voltage regulation testing parameters, and these are the parameters used to test the operation of this device, to do a characterization of the device, and we'll just touch on a couple of them. The output voltage from 7 volts to 20 volts will range from 4.8 volts, typical 5 volts, to a high of 5.2 volts, and then it'd be at 20 volts at 25 degrees centigrade. The input regulation needs to be 7 volts, remember 2 volts above the output to 25 volts, or 8 volts to 12 volts at 25 degrees centigrade. And this will be the amount of the voltage and how much it'll vary in millivolts per that. As a ripple rejection, to help you with your filtering cap, and the output regulations as the current changes from 5 milliamps to 1.5 amps at 25 degrees centigrade. That's how much the voltage will vary as the current changes. Has an output resistance of 17 ohms, 0.017 ohms, not 17 ohms. But as you can see, these are important parameters for your design as you're using it to build a power supply for whatever project you have. That's it for the characterization. Okay, our operating parameters for testing the 7810, LM7810 or the Micro A 7810 is as such. We're going to be, our voltage in is going to be 25 volts. It's 12.5 or 4 volts peak to peak coming in, our 12.5 peak, 500 milliamps. Our output voltage will vary from 9.6 to 10 typically, and the maximum of 10.4 DC volts out. That is at 25 degrees Celsius. It has an operating temperature, as the other ones did, from 0 degrees Celsius to 125 degrees Celsius, and will vary by this much. At the maximum, it'll be 10.5, and at the minimum, it'll be 9.5, typically 10 volts. The in-volt regulation is 12.5 volts to 28 volts. We have, it's got to be 2 volts above it, so it needs to be 2 volts above 10 volts, and we meet that criteria. And this is how much it'll vary as the input voltage varies coming into the IC. Has a ripple rejection of 120 hertz. The output voltage regulation from 5 milliamps to 1.5 amps at 75 degrees Celsius will be a minimum of 12 millivolts or a maximum of 200 millivolts. The thermal coefficient of the output voltage is a negative 1 millivolt per degree Celsius. And then the rest of this can be used as you determine how to bias your power supply to the circuit you're applying it to. Okay, that takes care of that. In our schematic of a power supply, the first part is a transformer, has a primary and a secondary. It steps down the voltage from 120 volts peak to peak to 12.5 volts peak, which is 25 volts peak to peak. That makes it have a turns ratio of 4.8 to 1, and that's all. I mean, that's practically all it does. It steps down a voltage to something we can manage and handle. The next section of the power supply is the full wave rectifier. And as you can see, it takes the peak to peak input AC voltage and forward biases on the positive, diodes like 1 and 3, and causes a positive peak to come out. Then on the negative pulse of the peak, it forward biases 1 and 3, 2 and 4. And so this being diode 1, diode 3, diode 2, and diode 4. And as you can see, it creates this ripple of output, consistent peak voltages. These are all 12.5 volts. That's why it's 25 volts peak to peak. These are 12.5 volt peak voltages, and it continues to do this over and over again. And that's it for the full wave bridge rectifier. The third part of the power supply is the bulk capacitance. It appears right after the full wave rectifier or bridge rectifier. As you can see here, this light blue line is your positive peak of the sinusoidal end, and it is half of the voltage that the sinusoidal peak to peak voltage was. Here's the negative side of that sinusoidal voltage, and again the positive side, and it just continues to go. As that filters through the capacitor, charging and discharging, the time constant of the charge rate of the capacitor is much larger than this bandwidth or this wavelength of the 120 hertz ripple. It's a 120 hertz ripple because it's 60 cycles in, and it's times 2, making 120. So you have the small ripple of 120 hertz. As we can remember looking at the electrical characteristics, it had a 120 hertz ripple rejection. This would feed and also into this would actually be an electrolytic capacitor, 470 microfarads, and it feeds into a 0.1 microfarad ceramic cap. The ceramic cap is for spurious spikes coming down the line, and it shorts all that to ground. This will feed right into the LM7810 family or the Micro A 7800 family voltage regulator. It will regulate it and output a nice smooth 10 volt DC regulated output. Okay, let's calculate our power dissipation so that we can see if we need a heat sink or not. We're going to be calculating PD using the formula PD equals VN minus V out times the current out. Our VN is 12.5 volts peak and the V out is 10 volts DC. Our I out is 1.5 amps. This is Ohm's law or the power law. And so this will come to 2.5 volts times 1.5 amps gives us 3.75 watts. Now we take this PD power dissipation and multiply it by the theta junction, and we know that that's 19 degrees Celsius per watt. And when it's the units for Celsius per watts, we multiply the P to PD, which is in watts. The watts cancel out. See that watt cancels this watt, leaving degrees Celsius. That's what we want here as our unit of measure, and it comes out to be 71.25 degrees Celsius. So we know that our operating temperature of this, well, we got our theta JA from here on the data sheet that we were looking at of the electrical characterizations of our 7800 family. And we also know that this family with a TO220 case has a 19 degrees Celsius per watt. That's where we got that from. And let me show you. And we know that we go to the 7810. That's the 75. That's the 8. 7810, and that the operating parameters temperature-wise is 0 degrees Celsius to 125 degrees Celsius. So if our power dissipation is above the 125 degrees Celsius, we must use a heat sink. So let's go see if it is. So we got the calculated power dissipation. We need to add it to the room temperature, which is 40 degrees Celsius, as just normal. But it comes out to be only 111.25 degrees Celsius, which is well under, not way under, but it is under 125 degrees Celsius. So we do not need to use a heat sink. The TO220 case has a heat sink on it, and it will dissipate enough heat to keep the thing from going in thermal shutdown. Okay, that's it. It's the end of the lecture. Well, we have one more thing. Then right after the 7808 regulator, you have another filtering, which is C3, C4, as you see here. They're just for additional filtering and to route any spurious signaling coming down. That's the end of this lecture. There's a couple things to remember I'd like to point out. To minimize heat and improve efficiency, use the lowest possible input voltage that still meets the minimum requirement, typically 7 volts. That's 2 volts above 5 volts. The electrical characteristic sheet said it was 7 volts. I said 9. That was my mistake. Low current, the LM7805, can typically supply up to 1 amp of output current, but this requires a sufficient heat sink. Without one, the thermal protection will shut down the chip if you go much above 1.5 amps. If you go above 1.5 amps, the thermal protection is going to kick in. So you need a heat sink. Component placement is important. Place the input and output capacitors as close as possible to the LM7805 pins to maximize their efficiency. Also, safety. The LM7805 has a built-in thermal and short circuit protection. The whole family does, making it robust against overloads. Okay, that's the end of that lecture. I hope you enjoyed it.